All right. Hey, Dr. Eldridge, thank you very much for joining me today on the Third Party Show. I've actually been really looking forward to catching up and having a talk. The area that I should say, a bit of an introduction. If I get this wrong, please correct me. But you're the head of the Department of Physics at Auckland University, and
That's right.
you are an astrophysicist. Is that correct?
I try to be, yes.
Okay. Yeah, a really interesting topic to be able to just sort of talk with someone about, I guess, about space in general, coming from a layman's
Yep.
sort of position. Could I ask you to give just a bit of an introduction about yourself and how you got into this field, and what was it that led you to the field of astrophysics?
I watched too much Doctor Who when I was younger. So there's a number of things that happened in the same year I was born. So Star Wars was released, A New Hope, in the year I was born, and then the Voyager 1 and 2 space probes were launched. So as I was growing up, there was all this fantastic science fiction on TV. So Doctor Who, Battlestar Galactica, Blake 7, Star Wars with all the toys, and yet also you've got the Voyager space probes that are going through our solar system and seeing Jupiter, Saturn, Uranus, and Neptune for the first time. And the other thing that happened is this was also the age when we had home computers for the first time. So like I had the ZX Spectrum and the Amstrad CPC. And so I've been using computers since I was about 5 or 6. Today, kids don't think anything of that. But you have this strange mix, therefore, when I'm growing up, of all this amazing science, people exploring the universe on telly, and yet also having a computer, because that's what's in those science fiction shows. And that's how you can now, that's the real tool that's changed science over the past few years. And so, I've been using computers all through my scientific career as well. So that's kind of like why I got into this, just because it's cool. And I didn't know how to have an academic career actually until I was about 13 or 14. I was at secondary school and they make you see a careers advisor. And I said, well, I was watching these Royal Institution Christmas lectures about physics, and I quite like physics, and physics and maths is easy. And I ended up therefore just going and trying to do physics. And you do your undergraduate degree, your PhD, and then you do a series of jobs until you get your permanent position as a lecturer. And I basically chose stars to study because they're cool. And at the time I was doing my PhD, there were people who realized that if we see a supernova go off in a nearby galaxy, a star exploding, you can go to an image you've taken previously with the Hubble Space Telescope and actually see that star before it exploded.
Mm-hmm.
And you can go, look, this star exploded. And so that's how my career basically started. And then I realized, well, if you study stars kind of, you've got to be careful worrying about stars because they make everything up. Well, astrophysically speaking, right? Because they make up galaxies in the universe. You could actually then understand everything else by trying to understand how stars make those galaxies and everything else up.
Yeah, it's amazing the field, stars themselves as something I try to, because I've got 2 little kids, trying to explain space and stars to them is really interesting because as an adult, you've kind of got a concept of what space is. But my son, who's the youngest, he still asks me, it's like, how big is it out there, Dad? Like, how many stars out there? Those stars, are they real stars? Those little ones we can see? Is the sun really a star? Heaps of these questions. Yeah.
But no, that's a really powerful thing, right? Just the concept that stars are other suns, and our sun is a star, is actually so deep. And there's this wonderful episode by Carl Sagan in his Cosmos series about stars, and he starts off and tells you the story where he first, had that understanding that the link between stars. But I mean, the numbers to answer that question are easy because there's about 200 to 300 billion stars in our galaxy, and there's about 200 to 300 billion galaxies in the observable universe.
Yeah, it's amazing.
So, yeah. So it's crazy. When I was little, I remember the first time I really had this concept of like how big things are. When I said, like, if we're in a room now and there's nothing around us, apparently, right, we can see right through it.
Yeah.
But we know there's air there. And that's quite funny because then you've got to go to a vacuum and think, okay, so if there's not this air, so anyway, that was just like that fundamental shift in your brain. It will happen one day. But yeah, it's hard. And I get used to these distances. And why kids, and you might be like, it's so big, it's 13.8 billion years old. That's how big it is in light years. And how do you understand that? And I just get used to it. But it takes a long time
Yeah, to get used to. It's the idea of a star is just an interesting concept. A massive, well, I'm going to get this wrong, of course, but a massive ball of gas and atoms fusing together, like they're under such gravitational pressure that they're just fusing in the center. That's what's going on all the time in them.
Yeah, yeah. I'm teaching this to my a fourth year postgraduate class at the moment, because that's when actually you've got enough maths and physics that you can understand it. Because to understand stars, you actually need all physics. Everything that we know in physics goes into making a star. Because so the sun is about 100 times the radius of the Earth, so it's 100 times bigger in radius, but it's 330,000 times more massive. And so because it's got that much more mass, it's got a lot more gravity. And you're right, stars are what you could call a gravitationally confined thermonuclear fusion reactor. The gravity holds it together at the center of the sun. Because there's so much weight pushing down at the center, it's got to get really hot. And that temperature at the center of the sun is 20 million Kelvin. So that's 20 million times, well, hang on, 200,000 times hotter than in this room, roughly. Although it is quite cold today. And what happens at those high temperatures is, you're right, you get hydrogen atoms, these like little protons smashing together to form, first they form deuterium, which is another form of hydrogen, and then they get another protons. There's a chain to build up towards helium, which is the next most stable element. And so stars are making star stuff, and that's the most efficient. There's only one process more efficient than hydrogen fusion for getting energy out of anything in the universe. And so that's why, we know that the sun has to be 4.5 billion years. If it didn't have nuclear fusion, the sun would only be 20 million years old. So the stars literally make new elements, and that's how they get their energy out.
Yeah, and so that's an interesting thing. If these stars, are they all doing the same thing? Are all stars fusing hydrogen? Because there's different types of stars. As a layman, I hear about different things, red dwarfs and white giants and that sort of thing. But at the core, are they all doing the same sort of thing?
At the beginning, yes. So stars will spend 90% of their lifetime burning hydrogen to helium. And when I say burning, this is the problem of being an astronomer. You use the word burning, and I actually mean nuclear fusion here, not like flame burning. And so yes, and there's a little bit of nuclear physics. So when we look at different elements, right? So things like hydrogen, helium, carbon, oxygen, the basic fundamental atoms. As you go up heavier, they become, for each, because they're all made of protons and neutrons, on average they get lighter as they go up towards iron. And so iron is actually the most stable element in the universe. And when you go beyond iron, they become, on average, heavier per little bit that goes in them. And this is actually where the energy comes from. And if you go from nuclear fusion up to iron, you get energy out. If you're going from, say, uranium or thorium, really heavy elements, towards iron, by splitting them apart, you also get energy out. That's nuclear fission. But stars will always do nuclear fusion, and they all go up towards iron. Now, our sun will, 90% of its lifetime, take hydrogen to helium. And then eventually it's going to have this pure helium core. And that will actually keep on heating up until it gets to 100 million degrees Kelvin, or Celsius. And then actually you start fusing helium to carbon and oxygen. And eventually it will do all that and just become a carbon-oxygen white dwarf, because it will take all the hydrogen to helium, all the helium to carbon and oxygen, and then that core will just become what we call a white dwarf and just fade away over the age of the universe, and nothing interesting happens.
And it won't produce elements any higher than the carbon and oxygen then? Will it stop at that?
It will do. As it dies, because you've got this carbon-oxygen core, and there's no, our sun will not be massive enough to do anything else. More massive stars can go further. Mm-hmm. But with our sun, you get the burning kind that happens in shells around that core. You can imagine it's like a little billiard ball where nothing's going to happen. But on the surface, it's still really hot. Yep. And those burning shells, this like flame, this nuclear flame going on around the star, can actually make really heavy elements by a different process. And you can actually get things like beyond lead, like bismuth, and uranium and other elements can be made by the sun, but in tiny, tiny amounts. And we know this because we can see, look at these red giant type stars, and we can see in their spectra elements that can only be made in the star because they're radioactive. They can't be there from the beginning of the star because they would have disappeared after billions of years.
Ah.
And so we can see that. The other fun thing we can do is if you look at asteroids and things that fall on the ground, normally they have little grains. And those grains have actually come from other stars. And you can look at each individual grain and they've got a different mix of elements and isotopes. And you can say, oh, this came from this star, this came from this star, but comparing it to our computer models. And so, yeah, they can make trace elements of heavy elements, but you actually, for all the other elements, you have to go to other types of star that are more massive and can evolve further.
So if all elements that we know, all the ones we've detected thus far, are generated in stars of some type.
Yep.
Yeah.
In stars normally when they die.
Right.
So, some of the heavy elements are made in stars like our sun when they're dying. The other ones, so if you have a star that's 8 times the mass of the sun, so if you took 8 suns, squeeze them together, you make what we would term a massive star. So anything that has more mass than 8 times the mass of the sun will actually die in a supernova. And those go all the way from hydrogen burning, helium burning, to forming carbon, oxygen, oxygen neon, neomagnesium, silicon, and up to iron. And so in their cores, they form an iron core that can't go any further. And actually that squeezes down into something you may have heard of called a neutron star, or sometimes a black hole. And when they do that, they release all this energy. And just like I was saying, our sun will have these burning shells and produce heavy elements. There's so much energy released in a supernova, you make, actually, explosively, you make most of the oxygen you're breathing right now.
Comes from supernovas.
And a lot of other elements. Comes from exploding massive stars, yeah.
And I heard that, is it Betelgeuse, which may go supernova soon?
Yeah, that's a perennial question. We don't know. It's really embarrassing. When a star's, it's difficult to model a star, and we can very easily model a star over its billion and million year lifetime. But when we start getting down to the last few years of life, or even the last few tens of thousands of years, things become uncertain. And the problem with Betelgeuse is it's the size of the solar system.
It's that big?
Yeah. So if our sun is 100 times bigger than us, this is about 1,000 to 2,000 times bigger than our sun.
Wow. I didn't realize that.
So
that's huge.
No, they're huge. So we actually have an image of Betelgeuse. You can normally find it online. And, you can actually resolve the disk. And the only reason we can do that is because it's so big. It's 500 light years away, but it's the size of the solar system. So if the Hubble Space Telescope, you can see its surface.
It's part of Orion. Is that where we see it? In Orion? Is it in the shoulder of Orion? Yeah.
Yeah, that's right. And Orion is a really easy constellation to find. And what's nice about Betelgeuse is if you compare it to the other stars in Orion, it's clearly orangey red, which is something not many people think. They think all stars are white, but actually they have different colors. The other one is Antares in Scorpius, or in Maui's fishhook. You can clearly see it's a red supergiant. And yes, you're right. This will explode sometime in the next 100,000 years. Some people say it could be sooner, some people not, but we really don't know. And there are a few other stars in the galaxy that we would see and have. If it explodes, we're probably safe, but we'll have this amazing display because
probably safe.
It's a really bright star. But it's an open question as to how close you need to be. We know that there is evidence in the geological record of Earth that supernovae have gone off nearby. And the elements produced have actually landed on a thin layer on the Earth.
Oh, wow.
It's only a thin layer, but we can see that, we know that happened, which is kind of exciting.
Yeah. So what would it be like if Betelgeuse did go supernova? You'd see it. You'd be able to see it? Yeah.
You'd see it. So it would be a type of supernova we call a type 2P supernova. So astronomers are terrible at naming things. Absolutely terrible. And when we first found these supernovae, which are like really bright lights, and if you work out how bright they are, there's something like in a few seconds, in a few days or months, they output as much light and energy as the sun will over its 10 billion year lifetime.
Wow.
But over a few days. And so when Betelgeuse goes, you'll have something about the brightness of the full moon.
Like all the time. So at night time, there will be this extra brightness in the sky, like the moon.
Exactly.
Wow.
Yeah. And for about 3 months, it will be the same luminosity. It won't dip. It will go through what we literally call its plateau phase. And that's because the material, when it expands, is so hot. This is the thing that all people always struggle with, right? So you've got this explosion. Explosions go bang. But at the same time, as this thing goes bang, it's going to cool down. So that material that's moving outwards, there's something where the light's coming from, which we would call the photosphere. But the bit where the bit we see would actually move inwards in mass, because, the material on the outside would cool down first before the stuff on the inside. But because the materials are expanding and they're cooling, the bit of light we see is actually constant.
Yeah.
And so for 3 months, because there's so much stuff coming out, it can actually last as a constant brightness. And then it will fade away, and we'll just see the light coming from the radioactive decay, because in that supernova, it's produced a lot of oxygen, but oxygen doesn't do anything. But also being produced is a lot of things like nickel, cobalt, and iron. And these are radioactive, and actually they then decay, and they give this what we call the radioactive tail to the supernova, and it slowly fades away. And we'll see that over months and years. And then after a few decades, Orion will look completely different.
Yeah.
We won't have this bright red star. There'll be a missing shoulder.
Yeah.
Someone will have cut his arm off. And we have no idea what we'll be able to see. But you may over time be able to actually see, even by the naked eye, the expanding supernova remnant of all that material, because that would end up being light years across as it expands out into what we term the interstellar medium.
So coming out of the supernova, or coming out of a star in general, like we say that there's elements, there's some of them producing iron and cobalt and nickel in a supernova. Is any of that in a solid form, or is that all just like individual atoms are fired out? Or after a supernova, if you were to travel there, would there be chunks of iron floating around? Or
no, but there will be dust. So stars produced a lot of dust, and actually one of the reasons why Betelgeuse is variable, and you may have heard a few years ago people getting really excited that Betelgeuse was going to explode, it was because actually it produced loads of dust. And when I say dust, it's actually like cigarette smoke. Okay, this is the only time when smoking is useful, right? Otherwise, it's bad for your health, right? But if you look at cigarette smoke, that's basically carbon-rich grains on a very fine particle. And stars produce it because the carbon and some of the other elements make little dust grains. And when you have enough of these, they actually block out the light. And then over time, you wouldn't go and find a chunk of iron, but you've got to think, this is where we take a step up in scale. So I've been thinking about stars. Now let's think about those stars within a galaxy. And so, as you said, they're pumping out material into the interstellar medium. That all mixes together. And eventually, it will cool down and then form the next generation of stars.
And
it's
planets as well, I guess. That starts to coalesce and form planets and things.
Exactly. So it's the dust and the gas all collecting together to then form the bigger blocks, which then form bigger blocks that then form planets.
So then are planets failed stars? Are planets just stars that didn't collect enough material to get heavy enough to draw in more material to get hot to become a star?
So that's a really interesting question, because how do you define a planet and how do you find a star? And if you find something that's the mass of a planet, but it formed like a star forms, is that a star or a planet?
Yeah, okay.
So stars and planets, the easiest way to try and think about this, form together. So you imagine this big gas cloud that's collapsing under its own gravity. Okay? And you find that the center collapses first, and that will form a star. And as everything keeps on collapsing down, even if there's a tiny motion in the gas cloud, everything spins up. And because, it's like that ice skating thing. So I've got a spinny chair, but I'm in my office, so I've got things around me and I can't spin. But in lectures, you stand out, you sit on a spinny chair, you hold your legs and hands out, and you spin yourself. And if you bring your arms and legs in, you suddenly speed up.
Yeah.
Right, so everyone should go and try and find a spinny chair and try and this. It's the same process, because even if it's not spinning when it's very far out, it spins up as it comes down. And the thing is, when you're spinning, you can't spin above a star, right? Because there's nothing holding you in place. So it naturally forms a disk around the star, and that disk feeds the star, but that disk is also where then the planets form, because there's still enough dust and gas, and it doesn't immediately get sucked in. So planets tend to form around stars in a disk, whereas the stars tend to be the thing that concentrates at the center. But there's a range of masses of gas clouds, and even within one big gas cloud, you might get multiple clumps all collapsing into different stars. And we know there are more low-mass stars than high-mass stars. And actually, it's like, where is that star? We know where the star-planet divide is in terms of mass, but in terms of formation, it's a really interesting open question.
So, because I've always been sort of fascinated by, I think it's Jupiter. Is it Jupiter, which it doesn't have it's not solid. They're the gas giants. Jupiter and Saturn, is it? They're the gas giants. So
Yeah.
you kind of always imagine science fiction, you could go and land on Jupiter, or you could land on Saturn, but you can't. It's just a gas. Yeah.
So I mean, that's the hard thing to try and imagine about stars and gas giants, is there isn't any solid core. The small caveat to that is that, of course, as you go down through the atmosphere, it's very gassy. But the second you start getting to the core, you start going into temperatures and pressures where really weird things can happen. And so, for example, at the center of Jupiter, there's a metallic hydrogen core, which is a gas, but it's compressed so much it acts like a metal. But yeah, you're right. There isn't any because I mean, even if you could go down that far, the pressures and temperatures would squish you.
Yeah.
So yeah, and stars are like that. Technically, they're a gas all the way through. It's not like there's a hard, solid, rocky surface. But of course, the temperatures are much more extreme than they would be within a gas giant. And you're right, Jupiter could be seen as a failed star, because if it was only a little bit bigger, if 10 or 20 times bigger, it may have become a star, and we would be in a binary star system.
I was going to ask, I've heard of those, and so that's just our luck, just like twins being born, you manage to get enough aggregation of atoms and dust, stardust, to form two new stars. It's an amazing cycle. So yeah, that's pretty cool the way that happens.
Yeah. Most stars, I mean, our sun is actually pretty rare to be on its own. So only about a quarter of stars, if you count up all the stars in the galaxy, a quarter are single, 50% are in binaries, two stars orbiting each other, and the other quarter are in triples, quadruples, quintuples. I think if you look on Wikipedia, like it's either 6 or 7 stars in the same system.
Wow.
Is the record holder.
And do they exist for long, or do they just like coalesce into one big star after a period of time? They drag each other in.
Well, yeah. So it's like the Earth and the Moon, right? This is a good picture, because the Earth and the Moon could be seen as a binary planet. Yeah. Right, because they're not too dissimilar in size. I mean, the Moon is a bit smaller than the Earth, but they orbit around each other quite happily. And actually, the orbit's increasing because of the tides on the Earth. Some of the energy in the orbit is being wasted in the tidal forces on the Earth. So, the Moon is, I think, like going away from us by like an inch a year or something.
Wow.
I have to go measure it. But so a binary star system is just like that. It's two stars. They're quite happy most of the time and orbiting around each other. But if you remember what I just said, like our sun one day and all stars use up their hydrogen and become red giants, that's when, as I love saying, they get in each other's way, because you've got this star all happy orbiting around each other, and suddenly it tries to become a red giant, and you're trying to squeeze both stars into the bite. It doesn't work. Yeah. And that's when sometimes they merge, sometimes you get a helium star, because if you've got that helium core and it's the hydrogen bit on the surface that expands and gets ripped off, you've then got a star of pure helium orbiting another star. And we see those, and they're quite exciting, because you can see their impacts in galaxies. And actually what's really exciting is literally we've never seen one of these helium stars. And last week, or was it like a fortnight ago, the people who I've known, Ulva Gottberg and Maria Drought, who found some examples in a nearby galaxy, published their papers saying, look, we found them.
Wow.
And it's just amazing that, like, finally, it's where you predict these models existed, and people have predicted them for like a century nearly now, that they must exist. And we found them. And then we can go, like, we don't have to argue with anyone anymore. We can say, look, these things really exist. Yeah. And that's kind of exciting. And the reason we know they exist is because with those supernovae, if Betelgeuse explodes, as I said, it's this type 2 supernova, which is hydrogen rich. We see other stars that explode that have no hydrogen. They're helium rich. And so, from that, but we'd never seen one that actually was like, there's a star that will explode.
Yeah, wow. So when we see, earlier you were talking about how we can see particles coming from supernova in the past on Earth, and you mentioned something else about other stars have different chemical compounds. So there was the Avi Loeb was talking Oumuamua. That's a really interesting thing. Have you been interested in that at all? Because it's an interstellar object, isn't it? It's not, the thing about Oumuamua, it hasn't come from our solar system. It's not an asteroid or meteorite from our solar system. This is something from another solar system.
Yeah. No, that's right. And how can we tell that it's coming from another system? And actually, it goes back to orbits. You know, this is stuff that Johannes Kepler, Isaac Newton, like settled centuries ago.
Yeah.
And actually, actually, it's wonderful maths and physics. If you actually work it out, it is, it's why calculus was invented, was to explain orbits. And so this system, I can never pronounce it. It came in, and we can tell from its orbit that it's got too much energy. It's moving too fast to be bound to the sun.
Right.
And so we know when it comes in, it will go out. And it does bring back memories because so there's a classic book by Arthur C. Clarke called Rendezvous with Rama. That actually, when you read the story, it's like, these two things are very similar. That's because they work out they've got this thing coming in, then they realize, oh, it's a funny shape. It might be artificial. And that's the big question about this interstellar object, is that it had a funny shape, right? It was like an elongated cigar because astronomers are very good at what we're doing. And when we find something weird, we look at it. And people were able to see that when you looked at it, its light curve, so how it changes its brightness over time, was weird. And it wasn't just like a sphere rotating. And you could actually work out that it was elongated. And unfortunately, many people, and there's some other things that are a bit weird about it, but unfortunately that led people like Avi Loeb and others to say, oh, it's aliens.
Yeah.
The one rule as an astronomer, it's never aliens.
Until it is.
And and if it was aliens, we would not keep it secret.
Yeah.
Right. I can tell you a couple of stories if you want me to later about how bad astronomers are at keeping secrets. Because like the most secret thing that people were trying to keep secret, and it leaked out on Facebook. Anyway. But yeah, so with this one, we're still trying to work out what it is and like how you would make something weird like this. But if we think to Arakoth, so do you remember there's this mission, the New Horizons mission to Pluto, and then it went on to another object, and Arakoth is this very distant object in our solar system that is basically two squashed pancakes stuck together.
Really? No, I wasn't aware of it.
So it's great because I remember seeing the flyby, and literally when you're flying into this, right, you see this wonderful, like, oh look, it's like a snowman. It's the two spherical things, and then they put the camera point looking at it as the spacecraft went by, and you go, oh, it's flat.
Wow, that is weird then.
So yeah, there's processes we don't understand how these things form in the distant solar system.
The Flat Earth Society must love this planet.
Its gravity is so low you wouldn't be able to stand on it; you'd float off. But yeah, I'm sure they do. So we literally don't know in our solar system or in other solar systems how you form these things.
Yeah.
And so that would be, it's got a funny shape, and there's many different processes that could have made that. And also it's traveled through interstellar space. We don't know what it's gone through on that journey.
Yeah.
So why it may have a different shape.
That itself is really interesting. But wasn't it also apparently accelerating when it shouldn't have been accelerating? And they're trying to figure out how is it, because it didn't seem to be emitting a corona like a comet, and they're trying to figure out how it could accelerate. Yeah. Yeah.
Well, there's many different things, but also it's like there's something called, I want to call it the Yorp effect. I'd actually have to go and look it up. But we know that radiation from the sun, just what I would term photon pressure or radiation pressure, can actually change and spin up asteroids and actually change their orbits.
Right. Okay.
So there is enough other things we can go to and try and understand that we don't need to say it's aliens. I mean, it could be, right? But it's always this case that extraordinary evidence requires extraordinary claims. Yeah. And what's really interesting in this case is it's enabled us to actually think, okay, so we have these interstellar objects coming through our solar system all the time. How do we try and get there? How can we say, okay, we've detected this one. Look, we've got this mission ready on the pad to go. We could actually send it.
Oh, yeah, and go and intercept it and study it.
Yeah. And it's very important for a number of reasons. So there's other things we can learn from them. So Michelle Bannister from the University of Canterbury, along with Chris Lintott and someone else, has looked at, if we look over the history of our galaxy and work out all the different comets and objects that may have been thrown out of solar systems, can we actually, by looking at these objects, understand something about the history of the galaxy?
Yeah.
And the composition of the galaxy, because maybe this thing is made of different stuff. It's going to be made of all the atoms we know, but a different composition. which maybe is why it had the acceleration.
So we can see here from Earth, we can see the Milky Way, which is our galaxy, and that's got, you say, was it 200 billion stars or something like that?
Give or take, it's difficult to count.
And then there's two other things, there's two or maybe one or two things in space that we can see that aren't in our galaxies, the Magellan Clouds.
Yeah, that's right.
And that's it. Everything we can see on a clear night, when you can see, all you can see is stars out there, they're all within our Milky Way galaxy there. Yep. And so Oumuamua could have come from one of those stars. Is that what we're thinking?
That's it, correct.
Yeah, okay.
Yeah. It couldn't have come from outside the galaxy, but you're right. So it's one of those other stars. And we have no idea when. The galaxy itself is probably just a little bit younger than the universe.
You're right.
So it could have been formed 10 billion years ago.
Yeah.
It could have been formed 10 million years ago.
Yeah.
We really don't know. But, this is one object. And actually, the thing is also studying one object, like studying the sun, tells you a lot, but doesn't tell you everything.
Yeah.
And that's why people are trying to find other ones.
I think it's interesting to try to understand how recently we've been able to study space, because I'm not involved in it at all, but just following bits and pieces of the news. Like there's the James Webb Telescope that's gone up recently, which is apparently very, very good and powerful. But that's the only James Webb. It's not like we've got 30 of those up there, and we've been doing it for 300 years with them in the sky. So we're still, maybe Elon will get us to Mars at some stage soon, but we're still, as far as we know, we've only ever gone to the moon. We've only ever put people on the moon. That's as far as we've gone. So much more to explore out there.
Exactly. I mean, they were going back to the moon, which is an interesting case. But the history of astronomy is interesting because, you just put together the space exploration and the astronomy. So, space exploration is really, going to the moon, kicking a rock and seeing it's there. But the astronomy is like trying to use the telescopes to peer as far as you can do.
Yeah.
And you're right, we've only got one James Webb, but we also have the previous telescope to that is still flying, which is the Hubble Space Telescope. And I think that's coming up for its 30th birthday soon, if I remember correctly. And, these have allowed us to peer back to the very edge of the observable universe. We can't go there, but we actually understand how the universe was formed 13.8 billion years ago. But we also have other telescopes. We have X-ray telescopes, we have radio telescopes. And you're right, it's really around about the 70s or 80s where it was because technology had advanced, we can build these bigger mirrors. So for a good astronomical observatory, you need a big mirror. James Webb has a 6-meter telescope mirror in space. On the Earth, we have many 8-meter telescopes now, which if you think like 8 meters, one piece of glass, that's a lot of bad luck if you break it.
Yeah.
But, the big telescopes allow you to collect more light to see fainter objects, but also resolve objects in the distance. So you can actually see finer details. And we're currently building 39-meter telescope.
To go into space or on Earth?
On Earth.
Right.
Sending it into space would be difficult. But that, just because of its light collecting power and its resolution it will achieve, will enable us to really actually even understand stuff that James Webb can now understand. We'll be able to see those in much greater detail. And it's interesting because it's always technological advancements that help us understand things. So, our current understanding of astrophysics and understanding of stars really started at about the 1920s. And it was all came about because of Pickering was this astronomer who got some funding from the widow of someone who enjoyed astronomy, Mary Draper, to make the Henry Draper catalogue. And if you ever see a star's name, it's got a HD number. And this is where those numbers all come from. But what Pickering found was that all the male assistants he hired to do the data analysis were terrible. And so he got the Harvard computers, who are people like Annie Jump Cannon, William Fleming, Antonia Murray, to actually analyze the data that the men could take in the telescopes. And they actually started to find out stuff like, what the temperatures of stars are. Finding the first binary star by seeing the shift in the spectral lines as the two stars orbit around each other. And then Celia Payne-Koposchkin working out that stars are made of hydrogen mostly, and not made of the stuff that's in the Earth. And so, it's basically about a century that we've started having this understanding. If you look how far we've come, and then that's just the stars. we've also understood the universe on the grandest scheme, because at the same time we was understanding stars, we was understanding that galaxies, are they part of our galaxy, like you just said, or are they like our galaxy but somewhere much more distant? And that knowledge is like, within living memory. Some people watching this may have relatives that would have been alive before we understood the size and scale of the universe.
Yeah. It's mind blowing. One thing that I think about, and I wonder if this is the biggest hindrance to people having interest in space, or if this is what gives people the interest in space, is daylight. Because during the day, all you see, you look up, it's blue, you see clouds, you might see the moon, but that's it. And you just don't think about it. You go on with your daily job. But even still now, I'm in my 50s, there's nights when I'll come home late or something and it's a clear night and you just look up and it just blows your mind to sit there for a minute and think, my God, we are so tiny. Like, we're right here. Like I said, we haven't even got off this rock yet to figure out any of what might be out there.
Yeah. I mean, it's the daylight's not actually the problem. It's actually the light pollution.
Yeah.
And so more and more of us are living in cities, and because more and more of us are living in cities, it means you have all this light pollution, so your eyes don't become dark adapted.
Mm.
And so there should be about 2,000, 3,000 stars you can see with your naked eye, and you can't see with them because your light pollution. The pro tip is, if you want to go to a dark site but you're scared of the dark, make sure you take a red torch, because if you turn on the red light that we have for bike lights, your eyes, they keep the dark adaptation. And actually, if you want to discover what the things are you're looking at, and you're looking at your computer, software programs like Stellarium actually have a red mode. So you can be using your Stellarium to work out what you're looking at, but again, it's in red. So your eyes remain dark adapted and you can still see the really faint lights.
What's amazing is the amount of satellites now that you see. I remember as a kid looking up and occasionally, living in Australia, occasionally seeing a satellite go past. Whereas now, we've actually seen one night, a year or 18 months ago maybe, we saw one of the Starlink chains going up, where there was just one after another going up. I can't imagine how many are up there now that you can't actually see because they're not reflecting light in the right way. But even the ones that you can see, they're just crisscrossing the night sky now. That must get in the way too, I suppose, of trying to observe what's behind them.
Yeah, it's huge. There are some ways we can try to mitigate some of the problems. But yeah, you can see lots of astronomers were posting images which have been Starlinked. And
like photobombed. They've just
yeah, exactly, because you just get the trail. Because to see a faint object, you need to have your aperture open and your camera recording for a long time.
Yeah,
and so you just see these trails coming through.
Yeah.
So you have trouble seeing them, and actually, New Zealand is actually really bad for this, because if you look at the orbit of the satellites, if you imagine, actually, I've got my Earth here. Hang on a minute. I've got a little toy Earth. So if you imagine the satellites in Starlink don't go round and around the Earth, they're in slightly inclined orbits. They go up and down as they go round, just because that it's the way gravity works and the way you launch them, that you can't launch them directly from the equator. But so they go up and down, and they spend most of their times when they're either low down or high up in latitude. And of course, because where New Zealand is, they spend a lot of time down here rather than when they're going across the equator. And it's really quite sad, because these people decided to launch the satellites without asking the rest of the humanity, right?
Yeah.
The sky, as you've already indicated and suggested, links us. We're all under the same sky. We've all got the same stars above us. And actually, it's just wonderful, because every culture has their own different stories. And I love learning, because when you grow up in a Western country, you learn about the Greek concept of all the constellations and everything. And then you learn, oh, hang on, the Chinese have something different. They have their asterisms. And actually, their records go back to millennia. So they have seen supernovae in their records, which, if you understand Chinese, you can still read and understand today.
Yeah.
But then, of course, we've got the peoples of the Pacific, Maori. They have their own understanding and concept and stories around the sky. And we all use them for the same thing, timekeeping and navigation.
Yeah.
And for a group of people to say, we're going to launch these extra stars. They look cool, don't worry. And not actually check, is this okay with everyone?
Yeah, well,
it's a bit sad.
It is a bit sad, because I feel, and this is just a feeling, but it's, I feel as though you're no longer alone. Like, you used to be able to, you go out the back when you were a kid, out in the bush, look at the stars, and you would feel like you were totally alone. Now, you can't help but see all these satellites go over and wonder, oh, are some of them actually looking at you right now, because I'm sure they've got the capability to do it, some of them. So, yeah.
Yeah. I mean, okay, this may sound a little conspiracy theory-esque, but astronomers have got a new telescope going up. It's a new optical telescope. I think it's the Nancy Grace Roman Space Telescope, or is it Euclid? Anyway, it's got a 2-meter mirror in it, which is quite a big mirror.
Yeah.
And the US government gave this to the astronomers because they didn't need them. And it's like, why have you got a 2-meter telescope that can go into space?
Yeah, exactly.
What are you looking up for? Oh no, you all want to look down.
Down, yeah.
So, you got to wonder why they have all this technology developed. Anyway, I'm sure they're not interested in us.
No.
But you can still get that experience. You've actually just got to go right in the middle of night.
Yeah.
Because the reason you can see these satellites is because during dusk, where the arrangement of the sun is with my light here, and if the satellite is still kind of here in orbit, you can still see it. But when it goes into the shadow of the Earth, then it becomes dark. So you've actually got to be really deep in the middle of night to be able to avoid the satellite.
Yeah. Okay. Yeah, that makes sense. What sort of things are you like studying or working on at the moment?
Too many things. So this goes back. Okay, so I study stars, and I study. When I did my PhD, I was studying the supernova explosions because I was making models of the stars that explode and comparing them to all these new observations that were coming in of the stars before they exploded. And actually, when I was doing that, I'm really lucky to have a very close friend, Associate Professor Elizabeth Stanway, who's at the University of Warwick, and we met it like the second or third week of our undergraduate study. And we did our PhDs both at the Institute of Astronomy at the University of Cambridge. And we were just leaving and we said, well, we need to stay in contact. Unlike normal people just saying, oh yeah, we stay in contact on Facebook and by email. Mind you, in those days, we didn't have Facebook. We said, hey, let's start doing some science together, as you do. And she was studying high redshift galaxies. So these are the galaxies at the edge of the observable universe. So like within the first billion years of the Big Bang. So very young galaxies. And I was studying things nearby. And it turns out galaxies are made of stars. And so we said, well, why don't we try and actually model those galaxies? Because from observations, there were things we didn't understand when we're looking at those stars. They had unusual spectra that from the models we had back then, this is about 20 years ago, you couldn't understand. And so we made this code that we call BPASS, which, okay, it's a terrible name, but it stands for like binary population and spectral synthesis. So what this means is we did what very few people had done before. We took lots of models of computer models of stars, something like 250,000, and we made populations of stars, like in galaxies. Mm-hmm. And we didn't just count up the number of different types of stars, we worked out what they looked like. So as if you were to put a telescope at this population, what would you see? Because then we can compare that directly to the observations.
Yeah.
And so that's really what we've been working on for 20 years. And because James Webb has been launched, it's seeing those most distant galaxies in ever finer detail, and actually pushed us back to within a few 100 billion years of the Big Bang, some of these galaxies we're looking at. And so we're trying to understand them. But at the same time, in 2015, there was this new window on the universe was opened through gravitational waves. So this is where, we're looking at light right now. If you're looking at a screen that's producing light electromagnetic radiation. Gravitational waves are when gravity does the same thing. But you've got to have very massive things moving very fast, very close together to produce them. And in 2015, the LIGO Observatory detected 2 black holes merging that were about 30 times the mass of the sun, and they merged together to make a 60 solar mass black hole. And those ripples in space-time are what they detected. When we looked at our code, we realized we had those binaries, those black holes within our code that we'd never looked at before.
All right.
And the cool thing is that we're kind of looping everything together now, is that these distant galaxies we're trying to explain with our models are actually where these black holes are formed. Stars died back at the edge of the observable universe, and they're producing the black holes today. And so we're in this big loop trying to link everything together, because if we look at the same models, which have the same physics from different ways, we can go, okay, that works. Okay, this looks funny.
Yeah.
We need to improve that.
So those black holes, when they form, do black holes exist forever, or do black holes stop? Like a star stops, goes supernova.
Yeah, yeah. So this is where it gets a bit tricky, because black holes are weird. So the black holes were actually first postulated centuries ago by, I think, Robert Cannon, who was a priest, who just said, okay, so if things have an escape velocity, right? Because I can get this ball, I can throw it up and it falls back down. If I throw it up faster, it goes up further. I can throw it up really fast, about 11 kilometers a second, and the ball will escape to infinity and never come back down. Black holes have so much mass in such a small space that nothing can escape, not even light, and you can't go faster than light. And so that's what a black hole is. And so we actually don't know what's inside it. And with our physics breaking down, we actually don't care what's inside it, because we're only worried about the surface. And so, yeah, black holes should stay and just be constant, because, everything gets locked in because nothing can escape. But there is this thing called Hawking radiation, after Stephen Hawking, who realized this, that near the event horizon, you can get some funny quantum mechanical effect, which actually means the black holes can slowly evaporate.
So they can leak energy, do they?
Yeah.
So,
yeah, but it takes trillions upon trillions of years for a black hole the size of the sun to actually evaporate. If you have a very low mass black hole, say something of a few kilograms, however, it would evaporate very quickly. And actually, if you've watched Star Trek and you have their quantum black hole torpedoes, it's actually because they have a quantum black hole that they then send off, and it's the black hole evaporating that actually causes the explosion. But otherwise, black holes will last for a long time.
They're one of those mind-bending things. Is like, what is happening there? Because we're so used to our perceptions of mass and material and having it exist in a form which is sort of constant to us throughout our life, to then think about it somehow being shrunk down to nothing, and lots of it being shrunk down to nothing into this little spot. Like, what is going on there? What is actually happening there? Is it sort of been turned back into just a potential field, and it's no longer mass? All the mass has somehow been turned into energy, and energy has just been turned into a field. Or is it a portal to another universe? I don't know. Yeah.
That's a very good description. The way you described it is actually, we don't actually know what goes on beyond what we term the event horizon, when the escape velocity goes to the speed of light, because we literally can't see inside it, because nothing can get out.
Yeah.
One way to try and get your mind around this is, let's look at the different type of dead star, right? Because the black hole is a dead star. They're normally formed in a very massive star, something about 20 times the mass of the sun and above. And actually, we don't even know if those stars go supernovae. They might just go straight into the black hole. But our sun will one day become a white dwarf. So that will be a ball of carbon and oxygen that's about the size of the Earth, but it has the mass of the sun. And so imagine where you're sitting, but the gravity is 330,000 times greater, because that's how much more mass it is. Right? That's pretty heavy. Now take that mass and squeeze it into a ball, not the size of the Earth, but something about the size of Auckland, something about 10 kilometers across. And so there the gravity goes up again by a factor of something like a lot. And in fact, neutron stars, which are these dead remnants of exploding massive stars, their gravity is so extreme. When you're looking at a face of it, if this ball was a neutron star, I would be able to see past the equator, because the light coming up here would be bent round. And so you can see something like 60 to 70% of the surface when you're looking at it, because of the way gravity warps the surface.
Wow, yeah.
And then if you go to a black hole, which if it was the mass of the sun would be 2 kilometers across, and you were to look at it, you would be able to see things behind it. And if you've seen the movie Interstellar, they've got this supermassive black hole that's millions of times the mass of the sun, but they have this disk of accretion going around it. So it's like a ring like Saturn, but you can see the other side of it, because the stuff coming off the disk gets bent round to your line of sight. Yeah.
So the idea of space-time, which, I guess most of what we all base physics on today, that there's space-time out there. Do you think about that? Like, space-time, my understanding is that people are challenging space-time now, that they're saying it's a very good model, but we don't think it's the complete model. So, what's next? What's after space-time?
Well, it's still there, right? Because every test of general relativity, which, so space-time is this concept that space and time are one. And you're right to say space-time. So I had one of my lecturers, Professor Malcolm Longair, would run around when he was teaching us about this lecture, just going space-time, trying to say it as quickly as possible together to get this thing that there's no hyphen. It is literally SPACETIME, and I hope I spelled that correctly, all in one word, because they're linked. And as I said, so this understanding of space-time is the best theory ever, because every test of it, these merging black holes, or like putting an atomic clock in an aeroplane, flying from London to Auckland, and seeing how much time passes, because A, the plane is flying and moving, so the clock runs slower, but it's further out of the gravitational field of the Earth. So the gravity is slightly different, and so the clock runs a little bit faster. Completely exact. Every time we test it, we know we're correct. So we can't really challenge it, which is the problem because it's so good. But you're right. It's what we term this classical theory. It's analytic. There's no graininess to us, because over the last century in physics, the two things that have really developed, one is general relativity to understand space-time, the very universe itself. And the other one is to understand the very small nature of the world, quantum mechanics. And so, stars only shine because of something called quantum tunneling, as well as like everything being really hot. The lights that are probably everyone's using, the light emitting diodes, are where you're actually taking energy from electrons and creating individual photons of a certain color. That comes about from quantum mechanics. Our entire world of telecommunication by optical fibers comes from quantum mechanics, which is where you're looking at individual packets of energy on the very small scales. We don't have that for general relativity. And so this is where the problem is, because we don't have that ability to turn what is a quantum theory of gravity. That's the thing we really need to be able to take our next big advance in understanding how the universe works.
Yeah.
And it's hard.
Yeah.
Because I'll tell you why it's hard, right? Because I've got this ball here, right? If I put this ball on the table, it's got the entire gravity of the planet pulling down it. Every atom and everyone else under is pulling down on this ball by gravity. And yet the electromagnetic forces, which hold my atoms together and make my arm move and all of this, can overcome the entire force of gravity and lift the ball up.
Yeah, I know. It's a very subtle balance, isn't it, between the forces of the universe to be able to do that. Oh, look, Dan, I know that you can't stay for too long today, but thank you very much. This has been a really fun, interesting talk. Maybe at some stage when you've got more time and come back, we can talk again and do this at some other time. But yeah.
Sure, no problem. Yeah. And it's probably good because, otherwise if you keep on going, who knows how many minds get exploded.
Yeah. No, I'd love to at some stage talk again. And, if there's some particular topics around astrophysics that you want to talk about, because I'm interested to learn on these sort of things. And I think people who watch the show, they'll find bits and pieces of this interesting for sure. So.
Well, if people ask questions, right, in the comments, then we can always come back.
Yeah.
And answer them at that point.
Yeah, exactly. All right. Okay, cool. Thanks,
you, Tim. That was great. Thank you.
No, you're welcome. It's nice to hang out for an hour.
Thanks.
Let me I'll stop the recording here. There we go. Yeah, cool. Thank you.